Across northeastern Egypt, one of the world's busiest maritime corridors intersects a landscape shaped by geological forces that have been quietly at work for millions of years. Every day, hundreds of vessels pass through the Suez Canal, carrying enormous volumes of global trade between Europe, Asia, and Africa. Few of those journeys give any indication that just beyond the canal lies an ancient tectonic rift that continues to adjust as the Earth's crust slowly changes shape. Why would a moderate earthquake in this region immediately attract the attention of seismologists? Why does an area that rarely appears in international earthquake headlines continue producing measurable seismic activity? Why are scientists closely watching faults that were formed millions of years ago, even though the most rapid phase of rifting has long since passed? Attention quickly turned toward northeastern Egypt after a magnitude 5.0 earthquake struck approximately 22 miles, or about 36 kilometers, northeast of Suez, shortly after midnight Coordinated Universal Time, on the 3rd of August, 2026. Seismic observations placed the source at a depth of approximately 6 miles or 10 kilometers, within the shallow, brittle crust where tectonic stresses are most commonly released through fault rupture. Although earthquakes of this magnitude are generally classified as moderate, their significance depends far more on their location than on their size alone. Occurring near one of the world's most strategically important maritime corridors, and within an ancient tectonic rift that remains geologically active, the event immediately drew the attention of seismologists seeking to determine which fault had produced the earthquake and what it revealed about the continuing evolution of the Gulf of Suez. Unlike many of the earthquakes that dominate international headlines, this event did not originate along one of the immense subduction zones surrounding the Pacific Ocean, where one tectonic plate descends beneath another. Nor did it occur on one of the famous strike-slip faults, where enormous blocks of crust grind horizontally past each other. Instead, it developed within the Gulf of Suez Rift, a broad zone where the Earth's continental crust is being stretched apart. That distinction is significant because the style of faulting provides valuable clues about the tectonic forces operating beneath the region and explains why earthquakes here behave differently from those occurring elsewhere in the Middle East. The epicentral area lies near the northern end of the Gulf of Suez Rift, the northwestern branch of the much larger Red Sea Rift system. Tens of millions of years ago, the Arabian Plate began moving away from the African Plate, initiating one of the most important tectonic reorganizations in the region's geological history. As the two plates gradually separated, the continental crust between them was placed under increasing tension. Rather than breaking apart in one enormous fracture, the crust stretched progressively until numerous faults developed, allowing large blocks of rock to move relative to one another. Over immense spans of geological time, those repeated movements created the elongated depression now occupied by the Gulf of Suez. The process responsible for shaping the Gulf of Suez differs fundamentally from the tectonic environments that produce many of the world's largest earthquakes. Instead of horizontal motion dominating the fault system, extension governs the region. As the crust is pulled apart, it becomes thinner and weaker until fractures develop. These fractures evolve into normal faults, structures along which one side of the fault moves downward relative to the other under the influence of gravity. Each earthquake represents another small adjustment along those faults as accumulated tectonic stress is released. Individually, these movements may amount to only a matter of inches or a few feet, or several centimeters to perhaps a meter, but repeated over millions of years, they have dramatically reshaped the landscape. For that reason, scientists do not attribute this earthquake to a single famous fault, comparable to California's San Andreas Fault or Turkey's North Anatolian Fault. The most likely source is the Gulf of Suez Fault Zone, an extensive system composed of numerous northwest to southeast trending normal faults that collectively accommodate the remaining crustal extension across the rift. These faults define the margins of the basin and continue to experience intermittent movement as regional tectonic stresses are redistributed throughout the crust. Identifying the precise fault that generated an earthquake within this system is often considerably more challenging than assigning an event to an isolated fault trace. The Gulf of Suez Rift contains many overlapping and interconnected fault segments, each capable of storing and releasing tectonic stress. Seismologists therefore rely upon detailed analyses of seismic wave arrivals, aftershock distributions, focal mechanisms, and ground deformation measurements to determine which segment most likely ruptured, even when an earthquake's epicenter has been accurately located. Additional scientific analysis is frequently required before researchers can confidently identify the specific fault involved. The earthquake's focal depth offers another important piece of evidence regarding its origin. At approximately 6 miles, or 10 kilometers below the surface, the rupture occurred within the brittle upper crust where rocks are sufficiently rigid to fracture suddenly rather than deform gradually. Earthquakes generated at these relatively shallow depths generally produce stronger shaking at the surface than deeper earthquakes of similar magnitude, because seismic energy has less distance over which to weaken before reaching towns, infrastructure, and transportation networks. While a magnitude 5.0 earthquake releases only a fraction of the energy associated with major destructive events, it remains large enough to be felt across a broad area depending on local geological conditions. One reason this earthquake has attracted considerable scientific attention is that the Gulf of Suez is frequently overshadowed by the neighboring Gulf of Aqaba, despite the two regions being governed by very different tectonic processes. Although both waterways were influenced by the separation of the Arabian and African plates, the Gulf of Aqaba forms part of the Dead Sea Transform, where the dominant motion involves lateral strike slip faulting. There, crustal blocks move horizontally past one another, producing earthquakes through an entirely different mechanism than the one operating beneath the Gulf of Suez. That distinction is far more than a geological technicality. It explains why earthquakes occurring within the two gulfs often display different faulting styles, different stress orientations, and sometimes different patterns of aftershocks. Within the Gulf of Suez, extension remains the dominant force. The crust continues to be pulled apart, faults accommodate vertical displacement, and the basin slowly evolves through repeated episodes of subsidence. Along the Gulf of Aqaba, horizontal plate motion controls seismic activity as neighboring crustal blocks slide past each other along the Dead Sea Transform. Although both regions remain tectonically active, they represent separate expressions of the complex boundary between the African and Arabian plates. Understanding why earthquakes continue to occur within the Gulf of Suez requires looking back through its long geological history. During the earliest stages of Red Sea formation, much of the separation between Africa and Arabia was accommodated within the Gulf of Suez Rift itself. As tectonic evolution continued, however, the principal zone of active spreading gradually migrated farther southeast into the Red Sea, where new oceanic crust continues to form today. At the same time, a greater proportion of the relative plate motion shifted toward the Dead Sea Transform, reducing but not eliminating tectonic activity within the Gulf of Suez. That shift did not render the Gulf of Suez geologically dormant. The extensive network of normal faults created during the region's principal phase of rifting remains deeply embedded within the continental crust. Those ancient structures continue to act as zones of mechanical weakness where regional stresses can accumulate over long periods before eventually being released through earthquakes. The magnitude 5.0 event serves as another reminder that even where continental rifting has slowed significantly, The tectonic forces that shaped the landscape have not disappeared. Instead, they continue to make their presence known through occasional moderate earthquakes that offer scientists valuable insight into the ongoing evolution of one of the Middle East's most important geological provinces. Although the Gulf of Suez no longer accommodates most of the separation between the Arabian Plate and the African Plate, tectonic forces have never completely disappeared from the region. Plate motion continues at an extremely slow pace, allowing stress to accumulate gradually along ancient faults that formed during the earliest stages of rifting. Rather than producing constant earthquake activity, these faults may remain locked for years, decades, or even centuries before finally slipping. When the accumulated stress exceeds the strength of the surrounding rocks, the fault suddenly moves, releasing stored energy as seismic waves. The magnitude 5.0 earthquake recorded northeast of Suez represents one of those periodic adjustments within a rift system that is still evolving, even though its most active period occurred millions of years ago. Ancient faults play a particularly important role in regions like the Gulf of Suez because they rarely disappear after they form. Once the continental crust has fractured, those faults remain permanent zones of weakness. Later tectonic stresses naturally concentrate along these existing fractures since reactivating an old fault generally requires less energy than breaking intact rock. That is why earthquakes continue to occur in places where continental rifting has slowed significantly. The landscape may appear stable on the surface, but deep underground the crust continues responding to forces generated by the slow movement of entire tectonic plates. Scientists have already gathered an important clue about the recent earthquake from its moment tensor solution, commonly represented by the familiar beach ball diagram released after significant earthquakes. While the graphic may appear complicated at first glance, it provides a simple answer to one of the most important questions following any earthquake. What type of fault moved? In this case, the solution strongly indicates normal faulting, matching what geologists expected for the Gulf of Suez Rift. Instead of showing sideways motion between two blocks of crust, the earthquake resulted primarily from vertical movement caused by extension. In simple terms, the crust was pulled apart until one side of the fault slipped downward relative to the other. That mechanism agrees remarkably well with the known geology of the region, where northwest to southeast trending normal faults have shaped the Gulf of Suez over tens of millions of years. The values accompanying the beach ball further support that interpretation. The calculated fault planes display steeply dipping faults with movement that is almost entirely extensional rather than horizontal. For scientists, that serves as another piece of evidence confirming that the earthquake occurred within the active Gulf of Suez Rift system instead of involving the neighboring Dead Sea transform, where earthquakes are dominated by sideways strike-slip motion. Although researchers continue examining seismic recordings to identify the exact fault segment involved, the faulting style itself is already consistent with the regional tectonic setting. For most people, the practical meaning is straightforward. The earthquake was not caused by two tectonic plates grinding past one another, like those responsible for many destructive earthquakes elsewhere in the Middle East. Instead, it resulted from the Earth's crust slowly stretching apart, allowing one block of rock to drop slightly along an existing fault. The actual movement during the earthquake was likely measured in only several inches, or perhaps several tens of centimeters, yet that small displacement released enough stored energy to produce shaking felt across the surrounding region. Earthquakes of this size are especially valuable to scientists because they provide fresh information without necessarily producing widespread destruction. Every recorded seismic wave improves the understanding of which faults remain active, how stress is distributed beneath the Gulf of Suez, and whether neighboring fault segments are accumulating strain. Modern seismic networks can measure ground motions far too small for people to notice, allowing researchers to reconstruct an earthquake in remarkable detail within hours of its occurrence. After an earthquake, attention also turns to aftershocks. These smaller earthquakes are not independent events but part of the same adjustment process. When the main rupture occurs, stresses surrounding the fault change almost instantly. Some areas experience reduced stress, while others experience a slight increase. Those changes may trigger additional small earthquakes, as nearby portions of the fault system continue settling into a new state of equilibrium. In many cases, aftershocks outline the portion of the fault that actually ruptured, providing scientists with another valuable tool for mapping structures hidden beneath the surface. The relationship between earthquake magnitude and fault size also explains why this event remained moderate. A magnitude 5.0 earthquake usually involves only a relatively short section of fault compared with the enormous ruptures responsible for major disasters. While the exact rupture length depends upon local geological conditions, the fault involved is generally measured in only several miles or several kilometers. By contrast, earthquakes exceeding magnitude 7 may rupture faults extending for well over 100 miles or more than 160 kilometers. The larger the rupture area, the greater the amount of energy released. Another important point is that earthquake magnitude does not increase in a simple linear fashion. Each increase of one whole magnitude represents approximately 32 times more energy release. That means a magnitude 6 earthquake is not merely 1 unit stronger than a magnitude 5, but releases roughly 32 times more energy. A magnitude 7 releases about 1,000 times more energy than a magnitude 5. This enormous difference helps explain why a moderate earthquake can produce noticeable shaking while remaining far less destructive than the largest earthquakes recorded around the world. Historical records demonstrate that the Gulf of Suez has produced moderate earthquakes many times before. One of the best known occurred in 1969 near Sharm el-Sheikh, when a magnitude 6.6 earthquake ruptured normal faults within the Gulf of Suez Rift. That event confirmed that extensional faulting remained active despite the gradual migration of the main plate boundary toward the Red Sea. Geological surveys conducted afterward documented evidence of fault movement consistent with the stretching of the continental crust. Another significant event occurred in 1992 when a magnitude 5.8 earthquake struck near Cairo. Although its epicenter was located north of the Gulf of Suez, the earthquake occurred within a transfer fault zone connecting the rift system toward the Nile Delta. It demonstrated that tectonic stresses generated by the interaction of the African and Arabian plates are distributed across a much broader area than the Gulf itself. Seismic hazards therefore extend beyond the obvious boundaries of the rift. Only 3 years later, a much larger earthquake struck the neighboring Gulf of Aqaba. The magnitude 7.3 event of 1995 was generated by the Dead Sea transform rather than the Gulf of Suez Rift. Unlike the recent earthquake, that event involved predominantly horizontal strike-slip movement as the Arabian plate slid northwestward past the African plate. Comparing the 1995 earthquake with the latest magnitude 5.0 event highlights the remarkable diversity of tectonic processes operating within a relatively small region. Although both earthquakes resulted from the interaction of the same major tectonic plates, they occurred on completely different fault systems and through entirely different styles of fault movement. Together, these earthquakes reveal that northeastern Egypt occupies a complex transition zone where different tectonic forces overlap. Some faults accommodate extension, others accommodate horizontal motion, and still others transfer stress between neighboring geological provinces. Understanding how these systems interact remains an important area of geological research because stress changes on one fault network may gradually influence conditions on another. The proximity of the recent earthquake to the Suez Canal naturally prompted interest because of the canal's immense strategic importance. Extending approximately 120 miles, or about 193 kilometers between the Mediterranean Sea and the Red Sea, the canal serves as one of the world's most critical shipping routes. Thousands of vessels rely on this passage each year to shorten voyages between Europe and Asia, making the continued operation of the canal vital to international commerce. Fortunately, the available seismic data provide little indication that an earthquake of this size poses an unusual threat to the canal itself. The epicenter was located several dozen kilometers away, and the earthquake was moderate rather than major, and infrastructure throughout the region is routinely assessed with seismic hazards in mind. While engineers continually evaluate bridges, ports, pipelines, and transportation facilities for earthquake resilience, moderate earthquakes such as this primarily serve as reminders that northeastern Egypt remains part of an active tectonic environment rather than signaling an impending geological crisis. The magnitude 5.0 earthquake ultimately reinforces a broader scientific reality. The Gulf of Suez may no longer represent the fastest-moving part of the boundary between Africa and Arabia, but it has not become geologically inactive. Ancient normal faults continue responding to slow plate motions, releasing accumulated stress through occasional moderate earthquakes that help scientists better understand the continuing evolution of this remarkable rift system. Each event adds another piece to a geological record spanning tens of millions of years, demonstrating that although the landscape appears unchanged from one generation to the next, the forces shaping it continue operating deep beneath the surface.